In this section, I'll talk about the concept of generative design as it relates to my own research and some of the other projects that we've been doing here at QUT and with colleagues at other universities. My research is into human-robot interaction and design robotics and using robots for creative outcomes. Generative design plays a really important part of this research. So this research started with a project that was funded by the Innovative Manufacturing Cooperative Research Centre, where we were working with an industry partner called UAP, a Brisbane-based company that manufactures art and architectural elements for locations all over the world. They have a factory here in Brisbane, as well as Shanghai and New York, and it's an amazing and highly successful company, and it's really a success story for Brisbane. It was founded right here. This image is the one I usually show when I explain what that project was about. It's a staircase from the University of Technology Sydney Business School, designed by the architectural practice Gehry Partners. And Frank Gehry was a world-leading architect known for experimental design processes. UAP, the company we were working with, builds art and architectural elements like this that are incredibly complex, often things that nobody else can build. They were commissioned to fabricate the staircase. So the practice that Gehry followed often involved taking things like crumpled pieces of paper, scanning them into the computer, manipulating them digitally, and then producing a 3D model that ultimately becomes a building or a staircase. Computer design tools are absolutely essential to this type of design. Gehry's practice has been a leader in adapting software from industries like aerospace to generate these complex architectural forms. For UAP, these designs would arrive as a pristine digital design file. And from that cutting-edge design process, they have to figure out a way to physically construct it. What's fascinating is that the fabrication process relied on uses techniques that are, in some cases, thousands of years old. The stainless steel panels were hand panel beaten, welded together by hand, and finished by hand. So there's a real disconnect between the sophistication of contemporary digital design tools and the realities of fabrication. So this was the jumping off point for our research. There was a need to help companies like UAP integrate robotics and automation into a fabrication process, making projects like this more feasible and sustainable. So through this project, I was very fortunate to work with some colleagues from RMIT. One of them, Roland Snooks, is an architectural professor and also runs his own architectural practice. And he creates extraordinary structures that are 3D printed, where the forms are generated using generative design processes. So one good example is Flow, an installation which was made for the National Gallery of Victoria. And the piece is meant to evoke the experience of an Antarctic ice flow. All of the panels were 3D printed by a robot, and Roland develops algorithms that generate these flowing forms directly from computer code. Here you can see a clear example of generative design. Computer code generates the geometry, and robotic fabrication makes it physically real. Another colleague on the Design Robotics project was Mike Shear, a structural engineer known for developing a technique called evolutionary topology optimization. With this process, you begin with a basic design, for example, a structural bracket, and then the software iteratively determines where material can be added or removed to optimize performance. The result is a structure where more material is concentrated in areas requiring strength and less material is used where it isn't needed. The outcome often looks organic or skeletal. It optimizes both weight and strength automatically. These optimized forms can then be 3D printed in metal, translating generative computer processes into physical outcomes. This is an example of work I did with colleagues from QUT, Miguel Teixeira, Glenda Caldwell and others, where we explored robotic cutting of polystyrene bricks. This project was created for the Istanbul Design Biennial originally and has since gone through several other iterations. We wrote software in P5.js actually that allowed us to generate black and white compositional patterns, and these compositions were divided into bricks. The digital data was then sent to a robot equipped with a hot wire cutter, which cut the shapes from the bricks, which were then assembled into a wall. At the biennial, the robot sat in the center of the installation. As it cut the bricks, the wall gradually was built up around it. I also want to mention that a former student from this subject, dxb211, Jared Gibson, worked with us as a research assistant. Based on what he learned in this unit, he programmed a 3D web-based visualization tool that would allow you to preview the structure of the tiles before they were cut. It's a great example of how skills from this course can translate directly into research applications. His work is shown there on the right. So these examples illustrate my current research focus on the crossover between digital generative design and digital fabrication. I'm particularly interested in what new possibilities emerge when generative computational processes are directly connected to robotic production. I'm curious whether you know of strong examples of generative design from your own creative practice. If you do, please share them in response to the question on the discussion forum. In the next part, we'll look at the programming concept of iteration and show some simple examples of how we can translate that for this generative design approach.